Okay, so at least that's going to be the comment. All right, so again, the area is 3 inches square, and we want to convert it to centimeters square. So 1 inch goes to 2.54 centimeters, right? So how do you convert areas? What you're going to do is you're going to write 3 inches square, and then you're going to do this, multiply by 1 inch is 2.54 centimeters. But I have inches square. So what I need to do is I need to multiply again by, again, 1 inch is 2.54 centimeters. See what I did there? Inches times inches is inches square, so cancels. Then the area will be the multiplication of all that. And then for that, you can use a calculator. 2.54 times 2.54 times 3. Okay, let's do a revision of what you're going to be doing in the lab. In the lab, you probably talk about significant figures. So 3 inches, as I wrote it there, I should probably wrote it 3.00, right? But 3 has one significant figure. 2.54 has 3 significant figures, right? So my final answer should have one, the minimum, right? The least amount on there. So I have here the answer. The intermediate answer will be 19.35 centimeters square. If you want to write in the correct number of significant figures, you will write, it will be accepted to write 19, but actually, believe it or not, some people will write it to 20. 20 has only one significant. This 0 on the right is not significant. All right. However, to make it more realistic, all right, this 3, I will do it like this. See what I did there? When you write it like that, these 2 zeros are significant now, right? The difference between 3.00 and 3 by itself, in terms of math, no difference. But in terms of science, physics, chemistry, even bio, it tells you how accurate your measurement was. So if you're doing a lab of this, remember, right? 3.00 has 3 significants. So then here, if I round this, so 3.00, 3 significants, the final answer should have 3 significants. So how do I round 19.35? I will do 19.4 centimeters square. This is actually more accurate. All right. So that's basically how you convert. All right. That should help you for some of those exercises that are in there in the worksheet. All right. Are there any questions about this? Oh, there it is. Any questions?
No.
Good. All right. Remember that the first quiz is going to be more conceptual, but there might be a question simple, just very simple about conversion. All right. I haven't decided when, but most likely it's going to be next week. All right. Your first quiz. I will let you know which topics, but starting with units for sure. All right. So I will recommend that you make a table. All right. Like the one I showed you last class, where you have your main units. Kilograms, meters, seconds, and then you have the prefixes, right? So millimeters, micrometers, nanometers, megameters as well, all right? I think those are the main ones. All right. And maybe a few of these that go from the imperial system to the international system. All right. So that's for the introduction of units. Let me just see. It's gonna take quick attendance here right now. Is Richard here right now? No.
Yes, I'm here.
Yeah. What about Miet Teresa? Therese? Jean-Pierre?
Yes,
Yeah?
yes, I'm here.
Okay, good. So
Yes, yes, I can hear you. Thank you.
Okay, so let's go into, let's close this. What is the other concept of physics that we need to introduce before we go directly into motion, which is going to be speed, time, velocity? We need to understand the idea of vectors. Now, 10 years ago, maybe even more, vectors was not taught in a school. In fact, even nowadays, it's actually kind of, it's not mandatory. But to understand the idea of physics, we need to understand the idea of vectors. So let's share the screen. All right. Let me show you the nodes of vectors and where you can find them. If you go to your canvas, this message here, that's why. I'm still not used to that warning message that they put in there because of the COVID. Anyway, so if you go here, we finish with this. So we're going into this, right? When you talk about in daily life, any number, any magnitude, like the amount of money, the time of the day, even the weight of a bag of groceries, right? Your height, those are scalars. They don't matter. They can have units, but there is not really a direction. Before we understand motion, we need to understand the concept of direction. If I'm moving towards you, I need to create a sense of direction. North, south, east, and west. The 4 cardinal points. Why is that important? Why does that matter? It matters because when you move at some speed or in certain direction, right? You are moving in a 4-dimensional space, universe. It's a 3-dimensional space, 4-dimensional universe. Probably thinking, what's 4 dimension or 3 dimension? 3 dimensions is what you are seeing right now, the X, Y, and Z plane. The easiest way to see it is right now you are in your room or in the living room. Just look at any corner and you will see that there are 3 lines that encounter each other. That corner represents the 3 dimensions, the length, the width, and the height, right? That's what you have here. So that gives you the volume of the room, right? If you multiply all of them together to get the volume. So the space where we live has 3 dimensions, but then we live in a 4-dimensional, at least as far as we know, we live in a 4-dimensional universe because we also have to take into consideration time. Any particle, any mass, any person in this planet or in any other planet, right? They move across space and time, right? Time passes as you move from one point to another. So that's important, right? So if I say I buy 10 kilometers to the store, you still cannot find the store. There's a good example there. You need to give where is the store located, in what direction. So you say 10 kilometers west. So what does that tell you? That the distance is vague. You know the distance is 10 kilometers, but to know where to go, where to find the store, you need to know the direction. Where is it located? In what direction? That's where this west comes into the play. So as soon as you add directions, this value changes from a scalar to a vector. Graphically, so let's stop sharing now. Graphically speaking, right, a vector is represented by an arrow. So look at this. A vector is an arrow. So there. It's a physical quantity that has magnitude and direction. So this is a vector V, and we label it with a bar. That is the difference between a scalar and a vector. A vector has the magnitude, so that's the length of this vector, 10 kilometers, for example, right? So let's say that's 10 kilometers. But the direction will be, well, for directions we need what? We are gonna be just working on the plane, all right? But remember that there are 3 dimensions, right? But in this plane, if I say this, north, south, east, and west, then I can say that this vector is going on the north, east. You know, you sort of talk about this when if you travel, or if you read a map, or if you use your GPS, right? You do kind of know about directions already, about north, northeast, right? About finding different places in the map. So you use it. So that's in some way an empiric way to introduce or to get to know what a vector is, right? So that's it. All right. Now, what is the relevance of this? Because a lot of physical quantities in physics are vectors: velocity, force, acceleration, momentum. All of those are vectors. Do we have scalars? Yes. Energy, power, right? Those are scalars. There is not really a direction. But for example, if I'm lifting this, right? I'm lifting this upwards. So I'm exerting a force upwards. So when we start introducing Newton's laws, right, we need to be comfortable with the idea of vectors. So then we can understand the magnitude and the direction of the force, right? And then for motion, obviously, we need to know if a mass is moving to the right or to the left, right? So let's look at the sign convention. So on the plane, you can have a vector going to the left or a vector going to the right. Let's call this vector A and vector B. Right? In fact, let's make it actually more simple, not A and B. Let's just put vector on the plane as well. Right? Let's draw this vector. There it is. That's vector A. Going to the right, and this will be vector B. These two vectors have positive directions. They are going to the positive. This is going to the right. So that's positive. This vector is going to the right and upwards. So it's right positive. A negative vector will be a vector going to the left. So if I want to draw the negative of this vector, I will just do this. The same magnitude, so the same length, but negative there. And for this guy, the negative of that guy will be this. That's important, right? So whenever a vector is going to the left, we consider as negative. A very easy way to see this is you can have one vector going like this. Let's say this is 10 units to the right, but then you have another vector here, which is 3 units to the left. The overall of these two, of 10 going to the right and 2 going to the left, the overall will be 7 to the right. Let's do one over there so you can see it again. All right. For vectors, direction is important now. So if you have 2 vectors, one is 4 units, the other one will be just 3 units. But then you have a vector in the middle, which is 5. The overall will be what? 4 and 3 are going to the right. So you say 4 plus 3, but then this is going to the left. So I subtract 5. And that will give me 2, but not just 2. 2 to the right. So what I just did here, I added vectors. When you add vectors, you can only add the vectors that are on the same direction. They can also be opposite directions. All right? They can also be opposite directions. But if they are opposite directions, you subtract. So in this case, these 2 markers are on the same length. So if I add them together, you get something like this, that one. But if they are going on different directions, they cancel each other. Okay? That's the idea with vectors. In terms of scalars, right? The way you add scalars is just your normal arithmetic way, right? So 4 watts plus 3 watts, 7 watts. That's the unit of power, for example, right? However, we are not always going to have a case where the vectors are conveniently on the same plane, on the same direction, right? We might have situations where vectors are on the plane at some given angles. So let's introduce vectors on the plane. Right? So we're going to introduce now vectors on plane. What does that mean? It means I can draw you a vector like this. This is the y and this is the x-axis, right? The x-axis, the y-axis, and then I can draw a vector here. Let's say vector A. When you have a vector like this, right, you have to find a way to express that vector in terms of x and y. And fortunately, there is already a way to do that. What we do is we draw this. We have here a right triangle. The only piece of information that we need to break the vector into components is the angle. It's an angle, it's called angle theta here. That angle there is the one that we're going to use to find AX and AY. These are the components of the vector on the x-axis and on the y-axis. let me show you the following before we solve that. If you go to the notes, right? If you go to the notes, here is what I drew. To understand the idea of vectors on the plane, we need to understand, or we need to remember, the Pythagorean theorem. The Pythagorean theorem gives you that the two legs, the addition of the square of the two legs, give you the hypotenuse square. And we use this. For example, look at this example, right? You walk 3 miles north, 4 miles west. How far you are from your location? So we're going to do that problem in a second. But before we do that, right? Let's see this. All right? And that will be the only math that will be introduced in this part, which at the end of the day is sort of like an application of the Pythagorean theorem. So if you have this triangle, so let's erase this for a bit. That's 90 degrees there. That's the angle theta. And this was the vector A. The way you're going to find this and this is the adjacent to theta. This is the opposite. So you're right here. Opposite, adjacent. What you need to remember is this. The sine of theta is the opposite over hypotenuse. And the cosine is the adjacent over hypotenuse. These are mathematical definitions that work only on right triangles. All right. So if I use that, then my AY and AX will be as follows. Let's put this in here. The AY, which is this, the vertical component, because it's the opposite, will be A sine theta. And AX will be A cosine theta. That's the only thing that you need to remember. All right? So that's how you break vectors into components. And that works for any vector on the plane. Right? So if you were to have another vector here or here, when we want to add the vector, right, you have to always find the components on each of the axes, on X and on Y. Okay? So that's important. All right? Now, let's see this one here, right? Let's apply this. Let's see in a word problem, it says that you walk 3 miles north, 4 miles to the west. All right. So to understand that problem, or that example, we need to draw the problem. So it says that you walk 3 miles north and 4 miles to the west. Right? So this is 3 miles, and all this is 4 miles. What is it says here, how far are you from your starting location? So you are here now, and you want to know this. You want to know this. This will be your X. North and west they make an angle of 90 degrees. So how do I find the x value in a right triangle? You will do the following. X squared equals to 3 squared plus 4 squared. The difference to what we just did is that 3 and 4 are the components already. They already use components, so you just have to find the resultant. We call this a resultant as well. All right? So x will be the square root of 9 plus 16, 25. So x is equal to 5, 5 miles. You are 5 miles away from your starting location. The other thing that you could be asked, actually, yeah, because it's here as well, just in case. The other thing that you could be asked is to find this angle. All right? If you are asked to find any angle, you just look at these values here. All right? Let's just use what we just did, like the concept of cosine or sine, right? The sine of theta is equal to the opposite over hypotenuse, right? And this is what you do in the calculator. So if you're using the calculator of the computer, let's share so I can show you how to use this. If you're using the calculator here, what is it? Oh, here it is. Right? You want to use a scientific one because this has this trigonometry, and then you say 4 divided by 5 gives me that, and then I do this, and I get the angle then in degrees, so 53 degrees approximately. All right, so that's kind of like the only math that might be in here. All right, I will probably just focus on the resultant. There. All right, and then you can always take a look at this animation here, right? What happens if you increase the magnitude of the vector? You see what happens with the components. It depends on the angle, right? So that's actually very interesting there. And some of the trigonometry that we did here today is in here as well. All right. So here is the vector and the angles. And here is the definition of sine, cosine, and tangent. All right. You probably only want to need sine and cosine, if anything. All right. And just in case, if we happen to do problems on the plane, this is what we will use. All right, if we end up doing that. Remember that the math is not the main part of the course. So the exercises for this, you can find them on the extra credit, right? So if you decide to do the extra credit here, so after the conversion of units, we do have a few problems, I think. Let's see, where you have to add vectors. All right. For example, this one is actually very simple. right? Let's try to do this so we can start going into motion. Chapter 1. So it says there, a player throws a football 50 meters at 61 north of west. What is the westward component of the displacement? All right. So for many of the physics exercises, you probably only need to apply one formula or one equation. But there are some situations like this, for example, in vectors, where it is very important that you draw the situation. All right. So it says there 50 meters at 61 north of west. So it's similar to this. What you will do is you first are going to draw your cardinal points. Let's so we have this. So this is north, south, east, and west. So the person, the player, is throwing the ball 50 meters, 61 degrees north of west. How do you do that? So that's north and that's west. So it's north of west, right? Will be here. So 61 degrees there. Okay. And they told you that it's 50, right? So all this is 50 there. All right. The question is asking you, what is the west? So what is the west component? What is this component, the west? All right. So if you look at the notes, or if you saw what we did on the board, right? It's there in some way, but remember, this is the adjacent of 61, and this is the opposite. I want the adjacent. So the westward component will be 61 because that's the adjacent, 50, the magnitude of the vector times cosine of 61. Here, right? This. And then you just use your calculator for that. So if you open a calculator, right? Or just use a scientific calculator, right? If you do cosine 61 times 50, you will get the answer 24.2 meters. All right. That's the only thing that you need to know, or the most advanced thing that you need to know on vectors. Of course, if we talk about vectors in space, it gets a bit more complicated because you have now 3 components. So that's the only thing that you guys should be familiar with, because we're going to talk about motion in the plane now. Then your cardinal points, right? Where is the north? Where is the south? Where is the east? Where is the west? Which is positive? North and east. Negative? West and south. Right? So technically speaking, that will be negative, right? The westward. But there are 2 ways you can write the negative. You can say minus 24.2, which is the answer. Or you can just say 24.2 towards the west. All right? The idea of a negative vector is not the same as a negative number, like an integer that you do in math. In science, they do need to have some sort of meaning. The meaning in this situation is the direction where it's heading at. All right? Other than that, I think that's a nice and sort of quickly, but we're going to be talking more about this now in the slides, but it's a good introduction to vectors. All right? If you have never seen this before, remember that you can always go into the notes, so that's why we have that in here. All right? Which are going to be very useful before you go into chapter 1. So units, we went on over units, so that's good. And then vectors and scalars. All right? Don't worry so much about the trigonometry, all right? Because again, that's just for you guys to know, but it's not one of the main goals on this section, right? The main idea is for you guys to know now the difference between a vector and a scalar, and that we use vectors to quantify physical concepts in physics, right? So, for example, displacement and velocity. Okay? Are there any questions? Any questions about these notes? Good. Remember that I will probably be offering office hours at some point between this week and next week, since you have your first quiz next week. All right. So if you need some extra information, please let me know. Okay. Anyway, so let's go into chapter 1. So now we can finally introduce the first chapter of this book and of this course. So if you go into the slides, you find this. Okay, let me ask you a question. So I've been talking about vectors, I've been talking about magnitudes, scalars, direction. Who can tell me in her or his own words, what is motion? Or what do we study in motion? Anybody?
Movement.
Movement, okay, good. And why is it important? Why do we care about motion? When you guys are driving on the road, have you ever been stopped by a cop? If you haven't, that's good, because they really like to stop you when you're in the freeway anyway. But if you are stopped, why do they stop you? Because you're speeding at some direction, right? So in order to know if you were speeding or not, you need to have what? You need to know your velocity. The way those radars work, they work by signals, sound waves that are sent between your car and the radar. And they use something called the Doppler effect, right? So they can actually, the only way a cop, and this is a hint for everybody, by the way, the only way a cop can be 100% sure that you were speeding is if the cop is next to the road, static. As soon as the cop is moving, there is a problem called relative motion. And also because the radar that he has doesn't work when he's moving. So they can just estimate by driving at the same speed as you are, right? But that's not very accurate. Not like the machine anyway. So remember that, right? So motion is the study of movement, right? Of distance, displacement, speed. That's interesting, right? I mentioned displacement, I mentioned distance, I mentioned velocity, I mentioned speed. We are going to learn in this chapter, and it's somewhat related to what we just did. The difference between displacement and distance. Let's start with that. Let's suppose you live in an apartment building. You go downstairs, so you are going to work, right? You live in the second floor. You go downstairs, but you forgot something, and you go back upstairs again. Can somebody guess what's the displacement in that case? You are going down and then up again. What is the displacement? What do you think, in your own words, is the definition of displacement? If you tell me that displacement is how much you went down and how much you went up, that's not correct. That's actually the distance that you travel. So for example, if you are going and running around a park, if you go for a run and you do laps, so you start at one point and you end at the same point, you travel a distance of 2 miles, 3.2 kilometers. Your displacement, however, I can certainly say is 0 kilometers. You're probably wondering how. How is that possible? Displacement is the definition of how far you are from the initial position. In other words, if you start at some point and you end up at another point, it doesn't matter what trajectory you took. The displacement is independent of that. The displacement is a vector. The distance is a scalar. So the displacement depends on where you are, in what direction. But the distance doesn't matter. Doesn't care about that. It's just the whole quantity of, right, of how much you moved. So that's what I want to start with. And that's something that you want to learn in this chapter. Okay? So here, to measure distance, right, we label it as D, sometimes as L, in some cases as H, if you're talking about a free fall motion, for example, right? And as you know already, we measure it in, there it is. Measure it in meters, right? But there are other units like millimeters, like prefixes, millimeters, centimeters, kilometers, and then in the imperial English system, foot, inches, miles, right? But remember, in physics, starting from last class and so on, we are going to be talking about SI units. Now, why are they important? So we talked last class and at the beginning of this class about millimeters, nanometers, centimeters. Why do we care? There you are. That's a penny. Yes. So the diameter of the penny in millimeters is 19 millimeters. But if I was to measure that in kilometers, look at the measurement there. So it's clear why we have different prefixes for different sizes. Depending on the size, depending on what you are measuring, we start using other units, other prefixes, powers of 10 per se, right? For example, for the nucleus of the atom, as I said before, we normally use nanometers or even picometers, right? So the size of the atom, the size of a red blood cell, that's where you start using microns, right? 8 times 10 to the negative 6 meters is 8 micrometers or microns. The typical height for a person, you can use meters. For the size of a building, you can still use meters. But as you go to the diameter of the Earth, the distance between the Earth and the Sun and so on, even kilometers stay short. So that's why you know, or you probably have heard, that in astronomy, for the solar system, we use something called the astronomical units to measure every distance within the solar system. An astronomical unit, just for you guys to know, is the average distance between the Earth and the Sun. Okay? So there you are. For the size of our galaxy, we start using what? We don't use a units, astronomical units. We use light years or parsecs. So as we go into higher dimensions, we start introducing other units, depending on the distances. Okay? The same happens with time, with area, with volume, and all that. All right? So we've done already conversions. So that's that for you guys. We did area conversions as well. All right? So this is if you have measurements in feet. And then, but we know in metric units, we're going to be using the square meter or meters square, centimeter square, kilometer square, right? And for volume, meters cube, centimeters cube, or, and this is very important, we actually use a lot in physics liters. That's because we use the advantage that the density of water is 1 gram per centimeter cube, or 1,000 kilograms per meter cube. So because we know that happens, we can use that to convert from meters cubed to liters. Right, there is a nice conversion there. And then for time, seconds, minutes, and hours, right? So we measure time, always going forward, okay? However, what do we have there? We have those old clocks. And you see the pendulum at the bottom? So how did that pendulum work to measure time? Let's suppose you let the pendulum go. One swing, so when the pendulum goes back and forth, that is called 1 period. So we can introduce the idea of period and frequency. Think in terms of not just the pendulum, but in terms of a wave that is going up and down. There is a periodicity on the wave. The same happens with the pendulum. So if the pendulum is going back and forth, we can measure the period it takes to do that. That doesn't give you the time, but it's measuring time units. It's measuring seconds. Let's take a look. Period is the time for one complete cycle of the process to be repeated. And then frequency, easy guys. Frequency is just the inverse of period. So it's the number of cycles per unit time. Okay? So the units for period, because it's measuring time units, is seconds. And frequency is the inverse of time, is measuring 1/seconds or hertz. And believe it or not, you guys, well, I hope, maybe not much nowadays, but you guys use that every day when you're in your car. Every frequency band in the FM radio uses those units. So when you see 93.7, 106.6 or something, that's normally in megahertz. So there it is, right? We're already using our prefixes because it would be too tedious and it would be kind of senseless to put 91,500,000 hertz in the touchscreen of the radio. We use the megahertz, or in some cases the giga unit there, gigahertz, right? Remember that 1 megahertz is 10 to the power of 6, a million hertz, and gigahertz is a billion hertz, 10 to the power of 9, right? So there it is. The frequencies for the AM radio are normally in kilohertz, so they are shorter frequencies. So that's why the FM radios are better quality. The larger the frequency, the more energy. So the easier is way for FM waves to go through, right? That's why AM radio is not very used much nowadays. So that's the equation there for period and frequency. Okay, an example of that will be this. You have a mechanical stopwatch that goes back and forth 10 times in 2 seconds. So what is the frequency? To know the frequency is the number of cycles per time. How many cycles you have in this example? 10. And what's the time? 2 seconds, right? So you just divide that. 10 divided by 2, 5 hertz. So the only thing that you need to remember here is the units of frequency, all right, which is 1/second. For the period, the only thing you have to do, guys, is you will write down the period, which is capital T, is the inverse of 5. And what's the inverse of 5? 1/5, 0.2 seconds. So that's the period. And that's important, right? The larger the period, the smaller the frequency. The larger the frequency, the smaller the period. They are inverse proportional. All right? So they are, when one goes up, the other one goes down. All right? Let's show you understanding. That, everybody, you're looking at the slides. When the period of the pendulum is less than 1, the frequency is always greater than 1. True or false? When the period of a pendulum is less than 1 second, the frequency is always greater than 1. Anybody? It's true. It's true. Any number less than 1 and greater than 0. Oh yeah, by the way, can you measure time or periods or frequencies in negative? Can they be negative? Can you have negative time? Unless you think that Back to the Future is real, which might be, but I mean, that's another area of physics. We're talking about like quantum physics in there, right? But in terms of classical physics, negative time is irrelevant, doesn't exist, it's impossible. So any number, any period less than 1 will be greater than 0. So we're talking about 0.5, 0.8, 0.6. What's the inverse of 0.8? It will be 1.25. So any number less than 1, the inverse of any number less than 1 is always greater than 1. So that's why if the period of a pendulum is less than 1, then the frequency will be greater than 1. Okay?
Okay.
What about that? Let's check your understanding. What do you think, guys, are the 3 fundamental physical quantities in physics? Anybody? It doesn't matter if you make mistakes now. That's what we're here to learn, right? So distance, we've been talking about it, so it's correct. What was that?
Number
I think
3.
the second one.
Huh?
The third
The
one.
second one.
Very good. Yes. Distance, time, and mass. There you are. Everything that we have around us, we can measure the distance, the time. Remember, right? We live in a 4-dimensional universe. The space and time. So the distance gives you the space and the time. And then the mass, not the weight. That's important now. It's going to this. Who can tell me what's the difference between mass and weight? Does anybody know what's the difference between the mass and the weight? if you guys did chemistry before, you will know, but if you didn't, let's just say that that mass is the amount of matter anything can have. For example, a pen is made of what? Made of atoms. And the atoms have what? Protons, electrons, and neutrons, right? But regardless, mass is the amount of stuff, the amount of matter, and it's measured in kilograms or grams. So what about weight? Okay, for that I need to do the board. So we know now that the mass of this can be measured in grams. But what's the difference between mass and weight? The difference between mass and weight is that weight is a force, it's a vector. So here is the Earth. All right? And you have a spaceship or anything here. It has a mass m. Because of the gravitational field of the Earth, the gravity of the Earth, that is being pulled towards the Earth. That's due to the force of gravity, that's due to gravity. This is the weight. The weight is a force, whilst the mass is the amount of matter. And the units are different as well. For mass, we use kilograms. For force, we use newtons. We will learn that next chapter. But there you are. All right? So when you guys are measuring the mass, if you're coming from South America, you will know that they measure it in kilograms, right? So that's the mass, that's not the weight. In daily life, we do talk about what's your weight. And you say, my weight is 65, 66 kilograms. Or in English units, 140 something pounds. But that's actually a force. That's actually the weight. Your mass, well, you will have to divide that by gravity, right? And what is gravity? Gravity is a constant depending on the mass of the Earth and the radius of the Earth. And we will learn that gravity is around 9.1 meters per second. Is the acceleration due to gravity. Is the reason why objects fall towards the ground. That's that, right? Also, mass measures inertia. The larger the mass, the greater the inertia. An easy example. Let's say you have a tennis ball and a bowling ball, and they both are coming towards you. You have a bowling ball and a tennis ball or a baseball. Which one will be easier to stop? The bowling ball or the tennis ball? If they are coming to you at the same speed.
They're the same, so at the same time.
No, the bowling ball is more massive. So, because the bowling ball is more massive, it will be harder for you to stop a bowling ball than a tennis ball. All right? Because it has more inertia. All right? Inertia is also the reason why, just a very easy example, right? You are driving and all of a sudden you have to stop because of a traffic light or something. You go forward, right? Why do you think you go forward? You go forward because of inertia. All right? That's Newton's first law. We will learn about that in chapter 2, but that's also a way to measure mass. All right, so we did this. All right, so we will leave it here today. Next class on Thursday, we will introduce the idea of speed and velocity. All right, and that's what we'll be using vectors again. So are there any questions about what we did today?
No.
Good. So what I will do if I were you guys is I will start taking a look at the web assign. Some of those questions you can already answer, the conceptual questions, and then we will do the numerical questions next class when we start talking about the relationship between distance, speed, and time. All right. That will be one of our first equations. All right. And I should let you guys know at the end of next class when and what will be included in your first quiz. All right. So let me just see here. 1, 2, 3, 4. Okay, so everybody was here today. Excellent. So remember, guys, the lecture was recorded. I'm going to stop the recording.